In the previous video, I introduced you to the formulas that we use to calculate the observed frequency of a sound wave in the case where the source of the sound wave is moving, but the observers are not. The change in the observed frequency of the sound wave due to the motion of the source is referred to as the Doppler effect. Anyways, getting to the formulas now, let's say that F sub S represents the number of compressions produced per time by the source. Let's say that the source is moving to the right at a speed V sub S. And let's say that over here we have an observer who is just standing there. The observed frequency, or in other words, the number of compressions received per time, would be equal to the source frequency divided by the quantity 1 minus the source speed divided by the speed of sound. Over here, we have another observer who's just standing there, but for this observer, the source is moving away from him. To calculate the number of compressions per time received by this observer, we use the same formula as for this guy here, except in the denominator, we put a plus sign instead of a minus sign. In this video, we're going to do an example in which we use both of those formulas. So let's say that we have two train enthusiasts. The train is moving to the right. So for the purple guy standing over here, the train is moving towards him. And for the green guy standing over here, the train is moving away from him. The purple observer reports that he receives 500 compressions per second. The green observer reports that he receives 300 compressions per second. We're going to say also that the speed of sound is 345 meters per second. From that information, we want to determine the speed of the train and also the source frequency. Let's get started by introducing some symbols to represent the frequencies observed by these two observers. So let's say that purple guy over here receives a frequency F1 equals 500 compressions per second. Let's say that green guy over here receives a frequency of 300 compressions per second. Now let's connect these two observed frequencies to the formulas over here. So the 500 compressions per second is for the observer who has the source moving towards him. So for this guy over here, we're going to use the formula with the minus in the denominator. We have then F1 equals source frequency divided by 1 minus source speed over sound speed. Now for the green guy over here, the train is moving away from him. So for the frequency observed by the green guy, we're going to use this formula here that has the plus sign in it. So we can write F2 equals source frequency divided by 1 plus source speed over sound speed. Now, if you look here, what we have is two equations and two unknowns. The unknowns are the source speed and the source frequency, and we have two equations. So why don't you pause the video and give this a shot on your own, see if you can solve the equations simultaneously to get one of these two quantities at least, and then once you've given that a shot, rejoin the video. So here's what I did. First of all, I'm going to number the equations 1 and 2. I'm going to rearrange the equations so that everything's in the numerators. So for equation 1, that gives me F1 times 1 minus Vs over C equals Fs. For equation 2, that gives me F2 times 1 plus Vs over C equals Fs. So notice now that I have two different expressions for Fs. Those can be equated to each other. So then I have F1 times 1 minus Vs over C equals F2 times 1 plus Vs over C. In this equation, everything is known except for Vs, so let's solve for that. I'm going to put the two terms without the Vs on the left. So I end up with F1 minus F2 on the left. To make everything super clear, I'm going to distribute the frequencies through the parentheses. On the left, that gives me F1 minus F1 times Vs over C. On the right, I have F2 plus F2 times Vs over C. So I'm going to start by putting the two terms that don't have Vs over C on the left. So I end up with F1 minus F2 on the left. Then I'm going to put both terms that have the Vs over C on the right. So I end up with, on the right, F1 times Vs over C plus F2 times Vs over C. On the right now, factor out F1 plus F2, all of that times Vs over C. So now isolating Vs, we get Vs equals C times F1 minus F2 over F1 plus F2. Let's substitute now. The sound speed is 345 meters per second. In the numerator here, I have the difference between the two frequencies. 500 minus 300 is 200 with unit inverse seconds. 500 plus 300 is 800 with units inverse seconds. So we get that the speed of the source, in other words, the speed of the train, is 86.25 meters per second. So this is a pretty fast train. Maybe this is a bullet train that you might find in Europe or Japan, but probably not the United States. Anyways, now that we have this, we can back substitute to get the source frequency. So look at equation 1 over here. It is already solved for the source frequency. We just have to pop in the speed of the train. So let's bring back equation 1. Equation 1 says source frequency equals F1 times 1 minus Vs over C. We then have source frequency equals F1, 500 compressions per second. And we have 1 minus 86.25 meters per second over 345 meters per second. Notice that everything in the parentheses here turns out to be unitless. So the unit that remains is inverse seconds. And punching everything into the calculator, I get 375. So the train whistle over here is producing 375 compressions per second, but this guy over here is receiving 500 compressions per second, and this guy over here is receiving 300 compressions per second. In the next video, we're going to explore what happens with the Doppler effect when both the source of the sound and the observer are moving.